Okay, welcome everyone. Let's wait a couple minutes just to make sure that we have as many participants as possible. So could you please type in chat plus if you can hear me? Let's check the device. Great, I see. So for those of you just joining us, hello and welcome. Thank you for joining us to today's webinar for Master of Data Science Online Degree Programs. Today we are offering industry webinar and our speaker is Andrey Zimovnov, Senior ML Engineer at Yandex. And just a little housekeeping before we get started. So as you see, we have a webinar format and it means that anybody who is participating can communicate with us. If you have any questions during the presentation, please type them into the Q&A box in your Zoom. I'd like to ask you to use Q&A feature because it will be easier for us to communicate and track your questions. And also it is great that everyone can see your questions and our answers. A recorded version of this webinar will be available in a few days. So I think that we can start. Andrew?
Oh, yeah, thank you. Hello, everyone. Today we'll talk about recommender systems and how we actually train them. So, as you now know, I work at Yandex, and more specifically, I work at Yandex Zen. That is a recommended news feed. So everything that I'll tell you today is something that comes from a hands-on experience and that we use in production right now. So the first question we have to tackle is to find out what is a recommender system. So I guess basically everyone understands what that is, but just to make sure, there is a good saying from CNN Money, just showing the basic difference from, let's say, a search engine. So CNN Money says that the web is leaving the era of search and entering one of discovery. And the difference is that search is what you do when you're looking for something, but discovery is when something wonderful that you didn't know existed or didn't know how to ask for finds you. So that is the basic difference. So everybody is doing recommender systems today. Everybody wants to predict what you like, what movie you will like, or what music track you would like to listen, or what article you want to read. So if you go online today, you can find recommender systems everywhere. For example, if you go shopping, let's say you type Amazon.com, you might see recommendations just on the product page. So it looks like this, like frequently bought together, and Amazon actually suggests that you can buy like these 3 books and they're going great together. So people usually buy them together. Or the saying can be like, customers who bought this item also bought something else. So one way or another, Amazon gives you like choice for new products, and they have figured out that these products go well together. So they're making a recommendation for you. Then you can find recommender system like on Facebook, for example. Facebook recommends pretty much everything. Maybe the posts of your friends, or maybe even new friends. So they can show you that their algorithms have figured out that you have a lot of friends and they have their friends as well. And maybe the friends of your friend, it might be your friend as well. So they can produce recommendations for you so that you grow your like social circle at Facebook, and maybe it will become more interesting for you. So then another example is TED.com, where you have related talks just under the video. So you can look for similar videos that I don't know, describe or explore the same topics, or they have the same speakers So one way or another, they're producing recommendations for you. And of course, the most obvious example is Netflix, because Netflix is well known for their recommender system, thanks to the Netflix prize that they had in, let's say, maybe 2008 or somewhere around that time. Netflix was ready to pay $1 million to anyone who can improve their recommendations by 10%. They have some measure of the quality, and that you have to improve it 10% to get $1 million. And actually, some people got it. They've made that improvement. So the place that I work at is it's called Yandex Zen. It's a news feed. You can basically it's an infinite feed that you can scroll for as long as you want, and it will be populated with interesting articles, interesting videos, or maybe even animations for you from all around the web. And Yandex Zen is basically a recommender system. That means that we've got millions of web pages online, and you don't have the time to see and to read like all of them. That's why we need to figure out how to choose like 20 or 50 most, I don't know, most like the best articles for you, so that you love reading them, and you love what you see on our site. And that's what recommender system basically does. It filters millions of options and tries to find like 10 just for you. And to make a recommender system know you actually have to have some browsing history, right? We should know something about you, like what sites you like to visit, what topics you like to read, and so on. So we try to take all that into account. Oh, I can see that we have one question here. Let's look at this. Oh, yeah, I guess that's not for me. Yeah.
I will answer.
Okay, so our main goal is to make the user love the recommender system. We can try to approximate like the measure of how much you love our system by measuring, I don't know, clicks or time spent, or how many likes or dislikes you give to our recommendations, and we take all of that into account. So basically, like recommender system tries to solve this particular problem. Imagine that you have this user item metrics where you've got a lot of users, maybe millions of them, and you have different items that you want to recommend. An item can be a movie, it can be a music track, it can be an actor, or I don't know, it can be an article from the internet. It can be pretty much anything. And this matrix is partially filled. So some of the ratings are known. And the rating, it can be just a number of stars. Imagine that this is, I don't know, IMDb, right? Where you can go and give ratings to the movies you like or dislike. And some of the ratings are known and they're there. But what you need to do is you have to figure out what rating will be like for this particular user. Like whether he will like that Sherlock movie that stands for the first column, or whether he will not like that. So that's where you have to make a prediction. And so basically the recommender system tries to complete these metrics so that all the ratings are known and we can make a recommendation. So I believe we have something in our chat. Let's look at that. Oh, alrighty. So one more thing that we have to know is that the rating that goes in that matrix can be of two different kinds. So there's an explicit rating, which is much simpler to use actually, because the explicit rating actually means that the user gives you an explicit feedback whether she likes that movie or not, or maybe that movie is somewhere, I don't know, above average or below average or just an average movie. And when you have that kind of feedback, you can actually understand that a user loves or dislikes that particular movie. But there is one more kind of feedback, and that is called implicit feedback. It is called that way because we don't really know whether a user loves that movie or not. The only thing we know is that user chose to watch that movie. That means that like he or she was interested in that movie, but we don't know whether they liked that. So that's why it's called implicit feedback, because we're not sure that you actually love it. So
I have several questions in Q&A.
Oh, Q&A. Okay, let's look at that. Is Google or similar search engines are a type of a recommender systems? You know, I guess it is pretty similar, but it tries to solve a different problem. So when you go to like the Google website, you actually have to have a query, right? You have to just find out what you need to type in to get something that you want. And you actually are searching for something like, I don't know, maybe seafood or restaurant, or I don't know, maybe you want to hail a taxi, and you just type in that query. And that is a little bit different problem, because that is actually a kind of information retrieval problem. You have to match that query to all the sites around the internet and find the most suitable. But in the case of recommender systems, you don't actually have a query. The user and his behavior is a kind of a query. It's a kind of a query, but it's different because it doesn't say explicitly what he is looking for, right? You have to figure that out with some sophisticated models, I believe. So actually we've got, wow, the questions are like pouring in. Is it possible to consider bias in rating by any person? Yes, it's possible. And by the way, when you look at explicit ratings, it becomes a kind of a problem, because some people can give ratings from 1 to 3 stars, like out of 5, right? They don't give 4 or 5 star rating because they know that I don't know, I'm waiting for 20 years for a good movie, a movie that will have a 4-star rating from me, right? And a 5-star movie is like a once in a lifetime for me. Yes, there are those people. And on the contrary, there are people that only give ratings like 4 or 5 because they think like, all right, 3 is like too little. Maybe that is a good movie, but it's just not for me. So there are different people with different biases and ratings, and there is actually a way to consider that. You can kind of normalize the ratings that users provide. You can actually subtract the average rating and divide that by standard deviation, and you will actually have a kind of normalized ratings for all the users. So it's actually possible. Okay, what kind of machine learning algorithms used? Basically, we use anything we can get our hands on, because if you look at the recommendation problem, it's actually just a special like setting for a machine learning problem. You can still come up with different features that you can engineer. For example, you can use matrix factorization that we will overview a little bit later as just an example of one feature. But you can have many of them. You can have neural networks. You can have like item-based collaborative filtering or anything like that. And then you can use your favorite gradient boosting like machine or any other algorithm on top of that to aggregate that ratings to the final score, which you will use for final ranking of your recommendations. So pretty much any machine learning algorithm can be used here. Alrighty, so keep in mind it is similar to reinforcement learning. Oh, I'm not sure it's pretty similar. I think that, by the way, today people are trying to solve recommendations with reinforcement learning. That is true, but as far as I know, it's far from being solved. So it doesn't help much. There are classical algorithms like collaborative filtering or matrix factorization that work better. So I believe that reinforcement learning here in this setting, in recommender system setting, it has future, but it's not yet there. Alrighty. So I guess we should go on a little bit, and then we will go back to the questions. Okay, so I've already told you that there are different algorithms that you can use for recommendations, and today we will overview two of them, the most popular ones like collaborative filtering and matrix factorization. So we will start with the first one, collaborative filtering. So what does that actually mean? Let's look at this simple example. Let's imagine that you have some users and you have some products, and maybe we are a grocery store and we need to recommend our users what they should buy next. The arrows that you see here, or the edges in this graph, actually mean that a user purchased an item. We don't know whether he or she liked an item or not, but the only thing we know is that implicit feedback that I decided to purchase it. So that's all we know. So it's kind of an implicit feedback. So if you look at this image, I believe you can come up with recommendations for Tom. So here we've got Tom and here we've got Rick. So what do you think is a good recommendation for Tom? Yeah, I can just read your answers in this chat. So what do you think is a good recommendation for Tom? So anyone? Kiwi, strawberry. So different answers, right? So maybe all of them are good recommendations, but the most popular one from the chat is kiwi. Let's find out why. So if you look at like Tom and Jerry, you can actually find out that their list of purchases is pretty similar. So like Jerry loves raspberry, bananas, purchased raspberry, bananas, and kiwi, and Tom purchased raspberry and bananas. So maybe they overlap so much because those users are similar. What if they are similar? That means that Tom hasn't discovered kiwi, but Jerry already knows that he loves kiwi as well. So that's why we do that recommendation for Tom. Maybe you should consider buying kiwi because very similar to you, Jerry purchased kiwi as well. So this is the logic behind this recommendation. This particular algorithm is called user-based collaborative filtering. That means that we try to make recommendations to our users based on user similarity. And in this particular case, we measure similarity by how much their shopping lists overlap or their order history overlap. So I believe I've got something else in this chat. Let's look at that. Okay. So now let's look at a different story. Let's look at Rick. So what do you think is a good recommendation for Rick? So let's split it in here. So what is a good recommendation for Rick? This is this crazy guy here. Strawberry. Alrighty. Raspberry. Kiwi is still kiwi, really? Okay, so raspberry and strawberry is pretty much the same thing, right? So the most popular vote here is strawberry or raspberry. So that means that that is most likely the right answer, right? So let's look at it. I think that Raspberry is a good recommendation as well, and I say that because I've made that recommendation based on the similarity of the items. If you look at these two items, Raspberry and banana, you can actually find out that the same users frequently buy them together. So Jerry buys banana and Raspberry, and Tom buys the same pair as well. So 2 out of 3 users have bought Raspberry and bananas throughout their history. So those two items might be similar. And that's why if we already know that Rick loves bananas, and we know that bananas are somewhat similar to raspberries based on the purchases of other people of our grocery store, we can recommend Rick to buy raspberries as well, based on the similarity of the items that we have in this graph. And this particular algorithm is called item-based collaborative filtering. And it can be actually used nowadays, and it can produce good recommendations. Alrighty, so let's try to figure out how we can measure that similarity. So here we said that, okay, similarity is just the magnitude of overlap. So if the shopping lists of 2 users overlap, that means that they're similar. But actually, it's not as simple as that. Let's look at this example. So that's frequently bought together block from Amazon website. We somehow need to, Amazon have figured out a way to measure that similarity of items. And the question here is, how do we calculate that frequency? So what that frequency really is it the absolute number of how many people have bought, let's say, the pair of these items, or what? Or how many people have bought it like in the last 30 days? So it's not clear how to calculate that frequency. And the basic idea is that you actually cannot measure the absolute value of how often they occur, how often you have that users that actually have both of them in their purchase history or their viewing history or whatever. In this case, it's purchase history because they're frequently bought together, right? So the basic problem with this metric, with just this absolute number, is that when you look at bestsellers like Harry Potter, you can actually find out that that book, it is called bestseller for a reason, right? So pretty much everyone have bought that book. And that means that if you try to find out how many co-occurrences Harry Potter has with some, I don't know, with a less popular book, you will actually find out that Harry Potter, based on that absolute value of how many people buy those 2 books together, like Harry Potter and some other book, you can actually find out that for that book, you have to show Harry Potter as a recommendation based on that naive count of co-occurrences in your history of your users. But that doesn't mean that Harry Potter is similar to every book, right? So if Harry Potter is a bestseller, it co-occurs with many books in users' histories, but that doesn't mean that it's similar to all those books. We have to measure similarity, taking into account how popular that item was. And if it was a bestseller, maybe it's not a good idea to recommend it to any book you have. So there is a way out, and I believe that some of you might know how to account for the size of those books, for how best-selling those books are. What do you think is the right way? How do we count co-occurrences here? Let's put it right here. So while I'm waiting for some options, I can actually look at Q&A section. Maybe there is something there. So what if it's a new user and doesn't rate it anything yet? Oh, yeah. That is called a cold start problem, which means that you don't have anything about that user, and you have to give him some kind of onboarding. You have to jumpstart recommendations for him somehow. And that means that you have to explore different options. You have to show diverse content. Like, I don't know, if you're recommending articles on the internet, maybe you should show articles about sports, politics, movies, pop stars, or anything like that. And you just see what is more what is more suitable for the user and based on the feedback that he or she provides you. Right after watching those recommendations, right? And there are different ways to solve that cold start problem. One of them is just to have a greater exploration, to show greater diversity in the content that you recommend, and try to just take a close look at the feedback that the user gives you for that particular feedback. Like maybe she likes sports, and she will click on sports and will omit everything else, and so you know where to go, right? So what else? As a student of biology, I'm curious to know whether such technologies can be used in research. I'm not really familiar with biology, what problems they try to solve there, but I believe that something based on similarities or like some clustering or matrix factorization can still be used there. I can just guess that there might be some problems like, I don't know, finding similar, like, I know, traits or similar people in case of their, I know, like DNA sequencing or something like that, or trying to find a correlation between those DNA sequencing result and I don't know, some illnesses or diseases or something like that. So machine learning in general is applicable there, and recommender system is just a subset of machine learning tools that you use for this particular problem, actually. So yes, I believe it can be used there. Okay, there is something else. So if some user has provided ratings for 5 movies in a month, then based on the average of ratings, when user will come back to the site, he will get to see recommendations based on past experience of ratings, right? Yeah, I guess that is exactly right. So if you give like 5 ratings a month to our system, we will actually accumulate all those ratings, and we will take all of them into account to figure out what you like most. So that is correct. So what is ALS? Actually, at the end of our webinar, we will overview ALS as well. It's alternating least squares. It's an optimization method used for matrix factorization, and we will get into that a little bit later. So yeah, I guess we can continue with those slides. Okay, you've got some options here. So number of items sold. You have to account for that to measure the similarity of the popularity of items. That is correct, but it's not so obvious how to take that into account in this particular metric. So how do you measure similarity between like books that you sell, and that similarity should be like based on 2 factors. First, how many people buy those 2 books together, and how popular those books are. Because if you don't account for popularity, Harry Potter will be similar to any book. So that's what we already know. There is actually a metric for sets similarity. It's called Jaccard similarity. And in our case, the set for an item is just a set of users that have bought that item. And imagine that A is a set of users that bought item like A, and B is a set of users that bought item B. And what we need to find out is whether those sets of users are similar or not. So whether those are pretty much the same people. multiplied by item A and item B, which means that those two items are pretty similar. So, for example, item A could be Harry Potter Part 1, and item B can be Harry Potter Book 2, right? So I believe that those are frequently bought together. And this overlap that you have in here, so this is the notation for sets overlap, that is pretty great. But what this metric takes into account is how big the, so let me hide that for a moment. What that metric tries to take into account is how much unique users you have in both of those sets. So these metrics is sometimes called intersection over union, which means that you take into account how big is the intersection of those sets, and you normalize it on, you basically divide it on the size of the union of those two sets. And if the union is pretty big and the intersection is small, that pretty much means that you have A and B of different size, and B can be much bigger than A. Or maybe A and B are of the same size, but they overlap, like they have a really small overlap. So either of those two things can happen, and that case with Harry Potter will be catched with this Jaccard similarity metric, because for Harry Potter, let's imagine that A is some not so popular book and B is a Harry Potter. The intersection will be big, but the union will be big as well, because Harry Potter is just massive. That's why the Jaccard similarity will be not as good for Harry Potter and some not so popular book. But if you have another not so popular book, B, of pretty much the same size, and it has a little bit less of an intersection with our book A, which is not as popular as Harry Potter as well, then Jaccard similarity can be great. So that is basically how we can deal with that. So let's look at our chat. Okay, couldn't you use genre or other features specific to the book or a movie? Of course you can. And actually that is like a different sets of algorithms. It's called content-based recommendations. You can look at the genres, or I don't know, artists, or maybe directors in case of the movies, or maybe even the description of the movie, just to decide whether that user will love that movie or not. So you can do that, of course. But this collaborative filtering tries to aggregate the interactions between users and items that you already have, and to make recommendations based solely on that information. So we don't use any meta information here. Alrighty. So you can also measure similarity for explicit ratings. So the Jaccard similarity is used for implicit ratings, because here we just have a set of users that purchased that particular book, right? But there is another kind of feedback. It's called explicit rating. And here it's a little bit, I don't know, I believe it is even easier. Imagine that you've got Tom and Jerry, and you've got on these like horizontal axis, you've got different movies. And some of the movies that they have rated are the same movies. But Jerry has some more movies that Tom hasn't figured out yet. So, and on the vertical axis, you have the rating, like on the scale of 1 to 10, how much you love that particular movie. And if you look at these two, diagrams, you can actually see something. You can measure the similarity of their ratings. There is a well-known, measure of similarity of these two curves. So how is that called? I believe that everybody knows that. We just need to recall that. So how do you know numerically that these blue one and this red curve are pretty similar? Yes, amazing. It's correlation. And basically correlation is all we need to measure here to find out that their ratings are similar. Correlation means that their ratings change in the same direction. So if it grows here, then it grows here. And there is pretty much a linear, linear equation that, like if this is X and this is Y, then Y is like proportional to X. It's like AX plus B. So it can be like that. All right. So if you've got that correlation, you can actually find out that you can produce recommendations for Tom. And you don't just have a set of items that you will recommend for Tom. You also have an approximate rating that Tom might give to those movies. And I believe you see that this correlation, just like in any other machine learning problem, gives you an opportunity to make predictions for the new movies for Tom in this particular case. So if ratings of Tom and Jerry correlate in their history, that means that they're pretty similar. And if they're similar, then we believe that their ratings will continue to correlate in the future. And that's why we can make this prediction for Tom. And we make prediction with explicit ratings. So we can just predict, like, I don't know, 10 here, 5 here, and 1 here. So we have that level of detail here. So that is the first algorithm. It's called collaborative filtering, and we've just scratched the surface, really, with that algorithm. But the basic idea is that you measure the similarity of items and users, and based on that, you try to produce predictions. So maybe we've got something on Q&A section. Let's look at that. So how to solve cold start problem in collaborative filtering? It's pretty much impossible to solve that in this setting, because for collaborative filtering, you must have some history of the user. Otherwise, it just doesn't work. You have to use different algorithms here for a cold start. You have to take into account the meta information that you have for your items, like, I don't know, the genre or the name of the book or something like that. And that might help, because you might find certain correlations in your data that users from particular region with a particular gender and age, they choose like books of particular kind. So you can observe that correlation, and you can use that to produce predictions for a cold start problem when you don't have any user history, but all you know about the user is maybe his or her login and age and something else that you have asked during sign up. Alrighty. So correlation is the right answer. What else? I believe we've answered that one. Okay, once again, how Kiwi was recommended. I'm not sure that this is still relevant. It was like 20 minutes ago. I'm sorry about that. Collaborative filtering seems to be quite explicit. It doesn't consider intent. I don't know what intent really means here. Like, if we know what you've purchased before, we can try to figure out what you might purchase in the future. And the intent of the system here is to drive sales and to give you something new and to sell more products. The intent of the user is maybe to find that system is easy to use. It predicts what he or she wants, and maybe the target action that we are aiming for here is to sell something. So I believe that the user should have like, I don't know, yeah, the user might have an intent to purchase something, and we just help him to find that. Alrighty, so what else? Oh, they're sorted like that. Should data set be big? Yeah, I believe it should be big. So if you have like 100 users and 1,000 of items, then you may not discover those great similarities in this setting. So you should have like, I don't know, 10,000 users maybe, or something like that, and like thousands of items. And these metrics should be completed by like 1%. So you should have approximately 99% missing values, and maybe less. If you have too many of them, too many missing values, then these methods don't work that well as well. Yeah. Can negative correlation be useful as well? Of course, if we know that two users are like they're non-similar, and they give like, I don't know, different ratings to the same movies, we can exploit that. We can exploit that, and the prediction will go not in this way, but it will go down if we know that Jerry and Tom have a negative correlation. So we can use that. So do surveys help in predictions too? Actually, we do something like that. Sometimes we ask users in their feed when they scroll it whether they love what they see, whether they are, I don't know, educated with that content, whether they believe that that content is relevant, it is, I don't know, it is fresh enough. I mean, it's something that can be said in the news or something like that, or it is an article from 2005. So we ask those questions, and we try to find out what users in general actually want. They want more fresh content, they want more diversity of the content, they want more educational content or something like that. But all of those is in general. It just gives us basic idea of where we should go. But to make personalized recommendations, you have to account for the actions that user make in your system, whether they read something, like something, or dislike something. Not all users love filling out surveys, so you can't actually account for that making recommendations. You can just have a basic idea of what's going on. Alrighty, so okay, one more. How to calculate a correlation between abundance of a species and their shelter preferences when shelter preferences are different, like arboreal and terrestrial. Whoa. That is a good question. I believe I don't understand it fully. Like different species, right? And they have different shelter preferences, and they're very different. Okay. So you mean that? All right. I think I got it. Like you cannot find two similar like species, right? Some of them live in the water, and some of them live in the, I don't know, in the rock, for example. Then you don't have, then you just can't compute similarity, right? Because they don't overlap, they don't have anything similar. Yeah, that is a kind of a problem. But if you look at the modern, I don't know, online shops or music recommendation engines or movie recommendations, you can actually find out that many people are pretty similar. So they've got, maybe there are certain stereotypes or something like that, but people are pretty similar. So if you love Batman, then a lot of people will love, I don't know, Spider-Man as well, because they are just of the same kind, and you can account for that. And you don't have so many options in case of movies and music. So I believe that's why these methods actually kind of work. But if you have a small data set with items or users that are very dissimilar, then these methods just won't work. But you never know. You have to try one just to make sure whether it works or not. I guess that is the best way. So okay, I guess we should move on. The one more algorithm that we really love is matrix factorization. So that is a pretty advanced algorithm, and we will have some some optimization problem here. Just be prepared for that. Imagine that we have the same matrix of ratings. We have users, we have items, and we know some of the ratings that they have, that a user gives to the item. And if we look at this, if we look at real problem, then you will figure out that this matrix can be pretty big. It can be like 1 million by 1 million, like 1 million users and 1 million of items. But the non-missing values, like that you have here, like constitute just a little percentage of all the possible locations in this matrix. For example, in real world problems, you have 99% of missing values. So you have a huge matrix which is filled with just 1% of cells. So 1% of cells is filled in this matrix. That looks like a waste of space, right? So a huge space for the numbers and just 1% of those spaces used. That's why people decided to compress that information. Maybe we can find out two matrices of smaller size that will produce the same ratings if we just take a matrix multiplication of these matrices. And usually in practice, this value of k, which is the size of this dimension here and this dimension, it is a pretty small value, like 50 or 100 or maybe like 200, but not as much, not much more than that. And m and n can be pretty big, like 1 million. And that means that you have this 1 million by 1 million huge matrix, and you've approximated that with a product of like m by 100 and 100 by n matrix, which are much smaller matrices. And that compression actually leads to generalization, and it can help us to predict what the missing values are. But first we have to figure out how to get these matrices. How do we find the values in these matrices, in matrix P and matrix Q? Actually, you can write an optimization problem here. An optimization problem, just to make sure that everyone is on track. So matrix product works like that. If you have this value here and you approximate it with a matrix product, that means that you have to take the third row of this matrix P, it is here in red, and you have to take the third column of matrix Q in here. So if you take a dot product of these two red vectors, it should produce the value that is highlighted in red here as well, in this resulting product of these two matrices P and Q. And a dot product of these two vectors is just an element-wise multiplication followed by summation of everything you've got. So it's just a sum of element-wise multiplication. So how do we find the values of P and Q? We write down the optimization problem like this. We actually try to minimize with respect to Q and P. So we will try different values of Q and P, and we'll try to find the minimum of this particular objective. The objective here says that the rating that you have, like for example this one, for this particular user, which is the third user, so the U can be 3, and third item, which means that I here can be 3 as well. So this rating must be approximated with a dot product of vector P in here, which is PU, and a column from this matrix, which is QI. And this notation actually means that you take a dot product of these two vectors. So we try to approximate that rating with the dot product of these two vectors. And we have a squared loss here because if you know like the basics of machine learning, then you might know that the squared loss is used in like simple linear regression, and this is pretty similar to what we're doing here. So we just want our ratings to be as close to our dot product in here as possible. Alrighty, and this summand is used for regularization. It's so-called regularization. Basically, it means that we don't want the values of P and Q to be huge ones, because if you have huge values in here, that means that their product is not like stable. If this is a huge value, then you have like a product of huge values, and you have an even bigger value, and it's not a good way to predict the value of 5. It's just, it means that some of them are hugely positive and some of them are hugely negative, but in the result you have to find out this small value, and this is not a good way to do that. So that's why people decided to do something like that. To minimize the our reconstruction loss with some addition of the fact that we don't want the values of Q and P to be big ones. So basically, this is how we optimize that. And I believe that you might know 1 or 2 ways to optimize that. So what do you think is a good optimization algorithm for this particular objective? So if you had that objective, what optimization algorithm would you use? So maybe you have some ideas here. And while we're waiting for some options, maybe we will look at Q&A here. Alrighty, let's start with the last one. LMS, what does that mean? Okay, there is something like ordinary least squares, like OLS, and maybe that is something similar to that. So L2 regularization is used here to produce better, it actually leads to better generalization, just like in linear regression or any other machine learning algorithm. So empirically, L2 regularization leads to better generalization, and there is, I believe there is even some theory on that. There is a very good blog post on L2 regularization. It is called A New Angle on L2 Regularization. It pretty much describes why you should have it and why it leads to better regularization with interactive plots. So play with that if you really want to know. So what else? How does a recommendation system remove old recommendations from the metric decision? Like movies someone watched 5 years ago, what is the trigger? Oh, that is a good question. I believe there is no exact answer to that. You actually have to try to engineer your features for recommender system, trying to take into account like the last year, last 2 years, last 3 years, and so forth. So you have different like predictions or different features. Like this matrix factorization prediction can be just one feature in your machine learning problem. and you can have a lot of them. You can take into account the history of any size that you have for your user, and the final machine learning model will be able to figure out which one should be used in every particular case. Yeah, I believe that you can do something like that. All right, so gradient descent. Wow, that is a good option. So we optimize this particular objective that we have in here with gradient descent. That is a good option. Actually, you can do gradient descent here and it will work just fine. But I've got one more algorithm for you, which is called ALS. It's pretty popular because it scales good. So if you have like really big data, like 10 million by 10 million metrics, and you need to factorize it as fast as possible, then you should go for ALS, I believe. So we will cover that in a moment. Yeah, stochastic gradient descent or backpropagation is pretty much the same thing. Alrighty, genetic algorithm can be used as well, but I don't know. I believe it will work for a much more prolonged period of time. You know, I think that you will not wait for that final solution of genetic algorithm. Alrighty, so too many questions, so little time. Quadratic programming or dynamic programming? Dynamic programming. So maybe, but believe me, the ALS algorithm that we will cover right now will do that much faster. So if you look at our objective, you can actually find out that that if you fix either Q or P in this objective, then the problem becomes very, very simple. It actually boils down to ridge regression. So if you fix the vectors of users, let's say this PU, for every user, you just fix that. You don't change that. You don't optimize for that. And all you want to optimize is the value of Q, like this item vector. This is QI, for example. And all you need to do is you need to solve this system of linear equations. You need to find the weights for this item vector in this item vector that will produce these ratings for our users, and that users have particular vectors. So that is basically the idea. We alternate fixing Q or P, and we optimize for the other parameter, and we optimize that solving the system of linear equations, which is a pretty standard task and can be solved pretty efficiently. So, but we have to start with something, right? So if we have, how do we fix the values of P or Q if we don't have them? We have to start with something, right? And it turns out that you can just start with random numbers. So you have a random initialization for both matrix Q and matrix P, and then in a for loop, in iterations, you do something like that. You fix users vectors and solve for the items with ridge regression, and then you swap them and you fix item vectors and optimize for the users. And if you do that like for 10 or 20 times, you can actually find that your objective decreased significantly and you've got great recommendations. So it scales good because if you look at this, you can actually see that the QI is only dependent on the users that interacted with that item. And if you fix users and optimize for the item, that means that you can optimize for different items on different machines or different cores of your CPU, and that can be done even faster. So it scales linearly, and it is a way to go if you have a big data, actually. Like that is the algorithm that we use at Yandex Zen to factorize a really huge matrix that takes terabytes nowadays. that's how it goes. Alrighty, so we have one more. Webinar keeps disconnecting. Oh, I hope that it's not for everybody. I believe it's your internet connection, so I hope so. Anyway, we'll have a video, so you can return to that later. Alrighty, so it is a convex optimization problem, so global solution is possible using least square error. Actually, so I'm not sure that is a convex optimization per se, because we have these product in here, but the basic idea is that we try to solve it in coordinate descent manner. So we optimize for Q, fixing the values of P. So anyway, we can actually, this is the algorithm that in practice reduces the error, because on every step of that algorithm, you decrease the error. You either decreases or it stays the same. Either way, it converges to some value. So I believe there is a formal proof on that. You can just Google for it, but yeah, it's a pretty solved thing. Alrighty, so and what those vectors that you have in here for items and users actually mean, they mean something. Like these 100 values, they actually depict your user or your item in some 100-dimensional space. But what is that space? It turns out that that is the space of some latent features of your users and your items. Let's look at an example of what that space might be. So here we have a two-dimensional embeddings, which means that we factorized our matrix with k equals 2. And these two values are actually coordinates in some two-dimensional space. Let's say that this is a space of fiction and comedy. The value of comedy, which is 0, means that that is something neutral. If it is positive, then that is something funny. If it's negative, it's something sad or not funny. And the same for fiction. So something fictitious and something very true to life here. And after training your factorization, your matrix factorization algorithm, you can actually find out that the vectors that you have for your items actually mean something. And similar items have similar vectors. And here you can account for similarity in terms of the angle that you have between the vectors in this space. So if you look at these like movies, you can actually see that Thor is pretty similar to Dumb and Dumber, because they have pretty much the same amount of comedy, and they have different fictionality, right? But they have the same amount of comedy, pretty much. So that's why they are very similar. If you look at Schindler's List in here, it's not a comedy, and it's very true to life. So it's something that points in a different direction in this two-dimensional space of these features that you have, like funniness and fictionality, I don't know. So you can just measure the angle between these two vectors, and it turns out the dot product that we have in here, like this is a dot product, like multiplication of these two vectors. This is actually almost the same as the angle between these items, if you account for the norm, for the length of these vectors. So it's pretty similar. And let's imagine that we have a user that likes Dumb and Dumber, loves Schindler's List, but doesn't like Thor. Where do you think the vector of this user points to? So where is the vector of that particular user? Where do you think it goes? minus y-axis. Right, it goes somewhere here because the vector of that user should be similar or close in terms of angle to the items that she likes and far away from the items that she doesn't love. So the vector of the user points somewhere here. It is somewhere close to the liked items. And what can we do with that information? So if we have the vector of user that points to that direction, we can actually produce recommendations because we have a lot of other items that this user haven't seen, and we can recommend that. For example, we might have a movie called Pianist somewhere here, which is pretty similar to Schindler's List. That's why it points to pretty much the same direction. And if we know that it's similar to the user in terms of the angle, then we can produce that recommendation. And that might be a good recommendation for that user. So that's pretty much the underlying intuition behind matrix factorization. The fact that it tries to compress the data, compress all the ratings you have, and it tries to find latent variables that describe the interactions of users and items that you have. And those latent variables can be treated as coordinates of vectors, and you can look at those vectors and find similar ones and understand why that actually works. So I believe that this is pretty much it. I want to just point out the few things that I think are the most important ones. If you look at the collaborative filtering algorithm, the basic idea is based on similarity of the users and items. And if you can calculate that similarity in any way, either using Jaccard similarity, Pearson correlation of ratings, of explicit ratings, or anything, then you can apply collaborative filtering and produce recommendations based on that similarities alone. But if you have more ratings and you have, like, for example, a lot of data, then you should go for a matrix factorization because it tries to compress all that huge amount of data you have just to find the latent variables, latent properties of users and items that you have. And these matrix factorization algorithm usually works better in practice, so I would go for it. And actually both algorithms are used today, and it's just a matter of which one works best on your data. And usually you have to try both to figure out which works best. But if you have a lot of data, go for matrix factorization. It's just my wild guess. Alrighty. So that's pretty much it. I've tried to cover the basics of recommender systems. We've just scratched the surface. There is a lot more to it. There is a whole world of neural recommendations, deep learning algorithms in there that are getting popularity. Maybe even reinforcement learning. Anything goes. But these two are classical algorithms that are pretty easy to grasp. And I hope you find that, I hope that was fun for you to know about them, or maybe to refresh your knowledge of them. So I hope that's useful. I believe we have a little bit more time, so maybe I will just go through questions here, maybe just to clear something out. So for the embedding and matrix factorization, if I know some of the attributes of user and some attributes of the movie, can I fill in the values of those and initialize random numbers for those that I don't have? Fill in Q and P, and then use the ordinary least squares to get optimized result instead of randomize all P and Q. I guess you can initialize that with something that you believe is important, but the thing is that if you initialize those with random numbers, it is easier for an optimization algorithm to find, sophisticated latent variables that will help to understand and explain all the interactions that you see in your user item metrics. So I believe that you shouldn't try to handcraft those vectors and fill them with attributes that that you might have, because that algorithm will find better ones. So you should just start with random optimization, and it should converge. It should work well. Yeah. So is Python a good choice for a language for big data problems? I don't know. I believe it depends on how big your data is. So if it's a matter of terabytes, you can still do it with Python. If it's, I don't know, a petabyte, then I don't think it can be done with Python. So you should go with something else, like Java, for example. So can we compare matrix factorization with PCA? Yes. As a matter of fact, PCA is done with matrix factorization as well. So today, PCA is implemented with SVD, singular value decomposition, which is a matrix factorization algorithm as well. So yes, they are very related. Talking about vector algorithm, if user likes just classic movies and watching simply all OSCO or words list having a huge differences in categories of each movie. Okay, so likes classic movies and just watches all Oscar awards, having a huge difference in categories of each movie. Oh, all right. So if the user is just the one that watches only Oscar awards, right? Then I believe it will be very difficult to find something for her or him based on the based on their history. Yes, that is correct. That would be a tough problem for our recommender. Yes, but maybe some Oscar movies are correlated as well. It can be it can be a case actually. So if there is some similarity, then our algorithm will try to exploit that. So is it cosine similarity? Cosine similarity is just another measure of similarity of vectors. Yes, we can use cosine similarity here. That is correct. Actually, cosine similarity is just a dot product divided by the norms of vectors, so it's pretty similar. Can you please let us know, okay, how do we do embedding here? Embedding. So embedding, actually, it is a term that comes from neural networks. It actually means that you give every user and every item just a vector of numbers, and that procedure is called embedding. You just put your user in 100-dimensional space. That's how you embedded them. Alrighty, so is it possible to recommend the times for more and less stuffing needs based on expected patient count, customer count? Oh, all right. So I think that is just like a classification problem, or maybe a regression one. It's just a classical machine learning problem. I don't think you have to boil it down to recommendations here. When you try to find a good time for the patient to visit, I guess you can do that with just basic machine learning stuff. Yeah, no recommendations here are necessary. Alrighty. I guess that is it. We've got a lot of questions, but we can't cover all of them. So sorry, everyone, if we didn't cover all of them. It's just a random choice. Thank you, everyone. So I hope you had a great time, and maybe you've got all that interested in recommender systems. I will go and read something about them. That means that my mission is accomplished here. So thank you again, and maybe we have to, I know, go back to our organizers. Maybe we have some closing remarks here.
Thank you, everyone. We appreciate you being here, and also I would like to say that the recorded version of this video also will be available. We will send you the links in a few days. Thank you once again, and don't forget to apply to our Master of Data Science degree program.
Yeah, thank you, everyone. Have a good day. Yeah. Bye-bye.